All right, looks like we're ready to go here. Can I get a shout out from the crowd there? Anybody hear me? Anybody hear me? All right, I'm back at the office here. Things seem to be working just fine. Today we're going to be talking about trees, and then tomorrow we're going to be talking about trees. This was a group of 3 lectures that we've tried almost completely unsuccessfully to squeeze into 2. So I'm going to be doing that here today and tomorrow, no matter what. What that probably means, however, though, is one or both of these lectures is going to go a little long, but it'll keep us on schedule. And a lot of times people are watching this in a different time, so that's not a big deal. If you do have an issue with leaving today right at noon, then make sure you come back and catch the tail end of the lecture if we go over. Sarite. Nice, one of my favorite slide pictures here is this one. This nice little, I don't know where it is, but it just looks great. Somebody do an image search on this and find me where this is. I'd love to go there someday. It's just peaceful and inviting. We're going to be talking about the fundamentals of trees. We've already discussed them just a little bit as we worked on some of the stuff for our binary search. Not our binary search trees, but for our binary heap, we had to have some tree basics in there. So some of this is going to be some real fast run-by slides to see if we can keep ourselves on time. But the context for trees is this great mathematical abstraction that allows us to take a lot of different situations and apply some common properties to them, as well as once we've got this tree structure defined and we start to build up, the design and analysis for how to solve them, it sort of takes this away from the problem itself. If you can take a problem and then represent it with a tree, then oftentimes there's a tree algorithm that will solve your problem for you. So in this particular instance, we've got one application of how a tree can work. We see that we've got operators and operands. This tree here logically represents that mathematical expression physically down there, x plus 3 quantity times y minus 2 quantity. And we've managed to put all of our operands that have 2 children, so these are binary operands. The plus sign takes 2 things to add together, the minus sign takes something to subtract from something else, and the multiplication sign there multiplies 2 things. So this is a nice binary tree here. We call them binary trees because each node has no more than 2 children. We talk about the graph consisting of a collection of nodes. We'll often call those vertices, and as well vertexes is also correct. So I've got something that's a vocal tic, then depending on what I'm thinking about, what I'm talking about, I've heard all 3 come out of my mouth. And that's not by design, it's just the way that it happens. Sometimes they're nodes, sometimes they're vertices, sometimes they're vertexes. All are correct. And we luckily only have one thing that we connect them with, and that's edges. So that's good. Each node can, of course, contain some data. We think of this tree as, here's 2 definitions for it. One of them is, it's a connected graph. All trees are graphs, not all graphs are trees. A connected graph without cycles. So that means that there's no nodes that are off on their own, nothing that's like an island. Everything is connected to everything else, but there are no cycles. So there's only one path from any one node to another node. Or the second definition here, we say a graph is, a tree is a graph where any 2 nodes are connected by some unique shortest path. The definitions are, of course, equivalent. In a directed tree, as we see over here, we see those edges have arrows on them that imply that the travel can go from A to B, but not from B to A, and so on. So in that case, we can identify these child and parent relationships, with the parent being at the beginning of the arrow and the child being at the end of the arrow, below the parent. In a binary tree, as I mentioned on the previous slide, each node has at most 2 children. It can have 0 children, it can have 1 child, but it can't have more than 2. The simple tree is the one we're going to be using most here. Sorry, now using most. That's our fundamental description there. We can see it over there with a bunch of red dots and nice. It's in Louisiana. Great. Probably never go there. There's edges as well, but that's a simple tree. And as we said before, this is at the very least a graph that has no cycles. So it's acyclic and connected, and a simple tree is considered undirected. So we can go from any node to any other node as long as they are connected. In a rooted tree, one that we use quite often is one where we've chosen, for some reason, a particular node as the root. And all of my edges then fall away from the root. Our CS trees grow downwards, whereas trees out in the wild tend to grow upwards. Of course, trees in the wild also grow down, that's the root. But mostly we think about the vertical above ground portion of the tree. In CS, we think of our root here starting at the top and then the tree growing downward. And so in our directed or our rooted trees, all of our edges are pointing from the top node downwards, or the root. Any node could be selected as a root. It kind of just depends on how that particular application is being done. There's nothing special about the root node in terms of its connectivity, is what I'm trying to say. Here's some more terminology, things that we've seen a bunch before that shouldn't be too much of a surprise. We've got the root, which is of course the topmost node of the tree. We've talked about the parent-child relationship, where we've got predecessors and successors. So the parent is the immediate predecessor of a node, the one that is directly above it. The child is the immediate successor of a node, the one that is directly below it. There are other relationships here. We see ancestor and descendant. So an ancestor is anything that is closer to the root than some node. So a parent is definitely an ancestor, just like in real life. But so is a grandparent or a great-grandparent. Those are ancestors, whereas descendants are something that is a child of a child in some cases, or it could just be a child. So a child is a descendant of a parent, but we do generally think of this specific relationship, parent-child, as the one-step version. The multi-step version here is covered by ancestor and descendant. So anything above would be something like an ancestor, and anything below we can see there as a descendant. Now, we don't think of ancestor and descendant working when we have to change directions. By that I mean you can travel up a ways and then travel down to get to it. In the graph on our right there, you'll see something like B and H, where B and H have the ancestor-descendant relationship, B being the ancestor, H being the descendant. But E and H, while E is above H in the tree, E is not an ancestor of H, because you have to travel from H upwards to B and then back downwards to E to locate. And when I say travel, I'm not talking about using the edges. I'm just saying visually we see that if I was going to connect those two, I'd have to go from H up to B and back down to E. And so you can think about this in terms of your real life. If you've got aunts and uncles, you can think of aunts and uncles. I always think of my aunts and uncles not as my ancestors. I think of them as my elders. They're in a level of the tree above me, and even that's not the case in some families. There's people that are at that aunt-uncle relationship that are at the same age or younger than their nieces and nephews. But in the general terms, we think of aunts and uncles, great aunts and great uncles as people who are elders, but they're not necessarily our ancestors because there's not a direct downward relationship to me. So in order for an uncle to get to me, we have to go up to our common ancestor, right? That common ancestor of an uncle is a grandparent, and then back down through your parent to you. So that's the distinction between siblings, between ancestors and descendants, and of course, elders. Siblings are, of course, same as they are in real life family trees, the children of the same parent. We see a pair of siblings there in I and F, both children of the C node. An internal node is, of course, a node that has children. So on this tree, there are a few of those. And then the opposite of that is a leaf node. There's only two types of nodes if we're thinking about it in that respect. There's either internal nodes, which has one or more children, or external nodes which have no children whatsoever. So there's a this tree is about evenly divided. I see 4 internal nodes, A, B, C, D, and then the rest of those are external nodes. We also call those leaf nodes. Leaf nodes are external nodes, a node without children. And this sort of extends the tree metaphor, whereas the leaf is the last thing that we see on the tree. There's nothing that branches off from a leaf because it's the most external bit that a tree has. We think of trees as recursive structures, so any subtree is just as much a tree as the original. Here there's a dotted line box surrounding this subtree that's rooted at 6, that has a couple of children and then a couple of grandchildren as well. But because this is a recursive definition, any node that has children, that's how we, and those children may have children as well, that's how we define a tree. So this is a tree that's rooted at 2, and there's a subtree that's rooted at 6, but it's also just a tree. If that's all I had, if I had a pointer to there, I could treat that with any tree processing algorithm I wanted, and it would process all of the information in that subtree as if it were a full tree all on its own. We've got some properties that we use to measure trees, of course. The height of the tree, that's the total number of rows here. If I look at that, I can see the total number of rows. And the thing about the height is we measure our height from a leaf node upwards. So our recursive definition says that the height of an empty tree is 0, and then the height of any node is the maximum height of its children plus 1. So in this case, we've got the max of height left child, height right child. That's because we've got a binary tree here in the picture. But this definition here really should be extended to say the max height of any child. So if we've got a tree that's more than binary, a tree that allows 10 children, for instance, we take the height of the tallest child, add 1, and that's the height of the parent. So we can see that height is measured from the bottom up. The opposite of that, of course, is depth, which is measured from the top down. So we say that an empty tree has got a height of 0. That's the base case definition. Then as we keep adding nodes, the depth of any one node is the depth of its parent, or in the case of the empty tree, 0 plus 1. So our root has a depth of 1, and we work our ways down. So all of our leaf nodes have a height of 1, our root has a depth of 1, and then they kind of blend their way across to the middle. So one thing to be aware of is even though height and depth are calculated differently, the maximum height and the maximum depth of any tree has to be the same. If you don't see that, work through these definitions and make sure that you do understand that. And then of course size here, that's just the total number of nodes. And that's a recursive definition as well. We can say that the size of an empty tree is 0. That makes good sense. There's nothing there. Then the size of any given node is the total size of its left child plus the total size of its right child plus 1. And that is, once again, implying a binary search tree. So I can say that the size of any non-binary tree, not binary search tree, just binary tree. The size of any non-binary tree is the same. It's just the size of all the children plus 1. Then the plus 1 is, of course, the node itself, right? So in this case, you see that the size of this tree is plus 1 for A, and then the total size of the subtree rooted at B and the total size of the subtree rooted at C, with that total size being the recursive definition that we're talking about. Here's our tree quiz. Answer these questions. What is the root? List the internal nodes. List the leaf nodes, also external. What is the maximum depth of the tree? Can we label any one subtree? And then this question, is this a binary tree? All right, I'll give you about 10 seconds. You should be able to get these pretty easily. All right, so jump into our solution slide here. We've got the root, of course. We all notice that as A. That's the topmost node that everything falls away from. And most of the time in our rooted trees, as drawn here, when you can really imply that the tree is rooted and everything sort of flows down from the A, we skip adding the arrows. It's just an additional bit of work to do as you're making illustrations. It's a bit of extra work to do while you're drawing things with a pencil to put arrowheads on everything. And if it's obvious that we've got a root and everything is flowing downward, we usually just skip those. It doesn't mean that we can travel up or down, or we can't. It's just that the way we generally write them is without arrows. When you need to make sure that it's clear that there's only one direction of travel, then you always put those arrows on there. But for the most part, it's implied that you're only traveling downward in a tree like this. Internal nodes, A, B, C, and F. Leaf nodes is, of course, everything else. D, E, G, H, I, J, and K. The maximum depth, where do we measure depth from? From the root. We say that the root is at depth 1, B, C, D is at depth 2, E, F, G, H is depth 3, I, J, K is at depth 4. I said the maximum height and the maximum depth have to be the same, so I'll start from anywhere. Let's start from D. D is an external node. It's got a height of 1, so is the height of A 2? Because it's 1 more than D? Well, it might be, but we have to take all of A's children and then add 1 to that. So we could add 1 to D's 1 to say that A is at a height 2, but that would be incomplete information. If we look at the tree that's rooted at C, we see that that's got a height of 2 because it's got leaf nodes G and H for a height of 1, and then C has a height of 2. So A has children C with height 2 and D with height 1. So I'll take the largest of that, 2, add 1 to it. I say maybe A is of height 3, but no, I can see that B has a tree there that's rooted, a subtree that's rooted at B that has a total height of 3 with those leaf nodes I, J, K. Their parent F has got a height of 2. B's got 2 children, one of height 1, the E, one of height 2, the F, the largest of which is 2. We add 1 to that. That makes B of height 3. So then A has children B, C, and D with heights 3, 2, and 1. We take the largest of that, 3, add 1, and the max height is 4, just like the max depth is 4. Labeling one subtree, this is an arbitrary answer. There are many of them. Here we've highlighted the subtree that's rooted at C. It's got children G and H. It looks like a tree. If I were to erase everything else from this diagram, you would still think that thing inside the green triangle is a tree. Last question, is this a binary tree? And the answer is no. We've already discussed A's 3 children, B, C, and D. We also see that F has 3 children, I, J, and K. And the definition of a binary tree is one where no element has more than 2 children. So this is not a binary tree. This is our fundamentals on trees. We've gone over a few of the definitions. These are things that hopefully you've already seen before, so we can breeze through them. If you need some more work with this, double back on that, but it should be pretty good. Up next, we'll discuss binary trees. We've already given you the definition of a binary tree. This is a tree that each node has no more than 2 children, but we'll talk about them a little bit more in depth. A lot of times, the things that we do can very easily be represented by binary trees. And we'll even look at a way to say, well, I've got a tree that's not a binary tree. Can you convert that into something that gives us a binary tree representation? And you've already done something like that since you've finished our project 2 with the pairing heap, which is a converted binary tree. As we look at binary trees, we think of them in a couple of different ways. There's an ordered tree where there's a linear ordering for the children of each node. As we look at them from left to right, the way that they get placed may be important. In an ordered tree, that ordering is taken into account. Of course, a binary tree, as we talk about this, is an ordered tree which every node has at most 2 children. There's a few different ways that we can implement this. Of course, we'll be looking at the 2 primary ways that we implement things in 281, which is in connected memory and contiguous memory. Here's one that, of course, we needed to do our heap. That's the complete binary tree property. That says it's a binary tree with a depth D, where everything gets filled in a row completely before we move down to the next row. So we're going to work our way from the top down, and before we go to the next row, we have to fill this row completely, then we move down. And then the way that we fill these things is always from left to right with no spaces in there. So these 3 sub-bullets here says a binary tree with depth D where the tree depths 1 to 2 to 3 to D minus 1 all the way up to the last one have the maximum number of nodes possible in all of those levels except possibly the last one. All internal nodes are to the left of the external nodes at depth d-1. So if there are some nodes that are existing without children at depth d-1, they have to be to the right of the nodes that do have children. And then all the leaves are at all the leaf nodes, all of our external nodes are either at d-1 in the leftmost area or at depth d. That's our complete binary tree. A few different ways to say it, but that's what we did with our binary heap when we represented that in contiguous memory. We talked about this as that contiguous memory representation, so I can do this with my root at index 1, then it gives me this very nice, easy math formula that says the left child of any node I is 2 times I, that's its index, and I can stick this in contiguous memory. The right child of I is 2 times I plus 1, and I can find those things in contiguous memory with a quick calculation and travel up and down the tree very quickly. Now, some indices may be skipped in the general case of a binary tree. Now, that's important. We didn't allow that in the complete tree, which was necessary for the heap to be efficiently implemented. But I can still do this with spaces. We need some way to recognize that a particular location may be empty. So you might have to have a traveling set of bools to say, you know what, there's a place in this contiguous memory for the left child of the root, but currently there is no left child of the left child of the root. So I'm just going to have to mark that as a false to say, don't look here for values, because even though there's memory that holds that data, what we're looking at in there is not actually good data. So that was how you could write this with some skipped indices. Of course, we looked at how the complete one was great because it sped things up, but it was also really nice because it kept our memory dense, right? We didn't need any more space than the total number of nodes that we have. So if we do allow skipping, then we can turn these contiguous memory trees into really large memory footprint with a sparse tree because we've got so many missed areas. So for instance, if I've got just a stick that goes 5 levels deep, womp, 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 I'm going to end up with something like 2 to the 5 minus 1 different locations in memory to take care of all of that business, even though I've only got 5 pieces of data. So it can be space prohibitive because we're using up so much empty space in a sparse tree. So we might not want to do the binary tree array implementation if we're going to have a tree with a lot of space as a sparse tree. As we look at the time complexity of dealing with the things here in the array implementation of the binary tree, we see that insert in the best and worst case range from constant time all the way up to linear. In insert, the best case, there's a place where we look, we stick it there. In the worst case, of course, we're trying to say I've got some left of left of left of left. I might have to go through all of those lefts to put on my newest item, which would make that linear. Remove key, of course, I have to find the thing. Generally, that's part of the problem. So that could be, in the worst case, a linear search there if I've got a stick to find the thing that I'm trying to remove. The parent is something that I can calculate quickly, just as the child is something I can calculate quickly when I'm using this array implementation. Just multiplying by 2 or dividing by 2 there gets me there pretty quickly. So I can get to, given any node, I can find its parent or child in a constant amount of time. In the best case, when it's really complete and dense there, I can get that space down to a linear amount. In the worst case, I'm looking for something that's 2 to the n. That's what I mentioned talking about having all of those spaces in there. My nose is itching outrageously. I don't know why. It's not because I'm not telling you the truth. I'm not lying. This is really tree stuff. My nose is just itchy. Okay. Now, let's talk about a connected implementation. So this is a pointer-based version of it, and we've got this nice templated node structure here, and this allows us to put any type of data that we would like into it. In this particular version, it's called key. You might think of this as data or whatever you wanted to call it. But the type is templated in, and the actual member is called key. In this struct, we've got this recursive definition. I mentioned the tree as a recursive data structure. It's recursive because it's usually defined recursively. So here I've got this struct node, but 2 of the members are node pointers. So I have to have a pointer to node. And the reason why we can do this, because it's got to have some base case. The compiler allows this because even recursive definitions need base cases, and the base case here is the fact that a node pointer is of a fixed size. There is always an 8-byte pointer on a 64-byte machine or 64-bit machine. So the compiler can know for sure that these node pointers are of a size 8 bytes no matter what. So then it can say it knows ahead of time what the size of this struct is once key is given. It's the size of key plus 8 bytes, and that's the total size of it. So that's our recursive definition and how it gets a base case, because a node is defined in terms of other nodes. Well, at least in this case, node pointers, and I've got a left pointer and a right pointer, and that's how I get to this binary tree implementation with pointer base, with connected memory. I'm just gonna take each one of these 2 pointers and point at some other node. I've got a constructor down here. That's a pretty fundamental constructor. It just takes the value and assigns it in there. We've got static initialization going on here in lines 4 and 5, which I do highly recommend. If you've got a struct or a class or something like that, and you know you've got some of these values that you want, have them in there. You don't have to put them in the constructor, but they do have to be initialized. That's fundamental. When you're making a data object, you have to initialize everything. Everything. So you can do it either by sticking it into the constructor, or you can do it by sticking it in static initialization. And that's where I say in lines 4 and 5, node pointer left is equal to null pointer. That's statically initialized because it's initialized here at compile time. And it knows that every time I create one of these things, we're gonna put a null pointer in for those 2 values. Now, my constructor need only fill in this key, right? And since this is templated, we can't really say, well, key is always equal to 0, which is something you might do if you were building something that was non-templated. Maybe if I had a set of integers with pointers, I was building an integer-based binary tree, I would say key is equal to 0, so that I at least knew it had some value. But even then, values are hard to define as a default level in most cases for your trees. So you want to make sure that at the very least that your pointers are all under control, because that's where memory goes bad. Valued problems are usually pretty easy to track down. They're usually a lot easier to track down than pointer problems. So you save yourself a lot of pain if you make sure that you initialize them either statically or in the constructor. Constructors are for that. Constructors are for making sure that once we get done with the constructor, everything is initialized. Please, please, please do that. You will thank me and you will thank yourself for getting it done. In this version of the constructor, all we're doing is initializing that key with this incoming constant reference to a key K, and there's an initialization list there, which is after the colon and before the curly braces of the function over there. So this assigns key to be a copy of that K value there, unless of course key is a reference to keys. But that's the getting into the details there. But this is a nice constructor that we can, this is a custom constructor. We can't, because this object does not have a default constructor defined, which is probably going to give you some problems here. So it needs a default constructor if you're going to make any of these, just by saying I'd like to have a collection of them, and then it creates them all at once by calling their default constructors. If you're never going to call the default constructor, this will work, but this is just a custom constructor because you have to pass in a value to make that work. So the node has some information, of course, that's the key, and then it points downwards to its left child and right child nodes. Very efficient for moving down, because we can always just jump down a pointer and be at the left child, or jump down a pointer and be at the right child. It's not so great for moving up. It's actually impossible to move up a tree. How do we manage this? Most of the time our algorithms that involve this type of data structure end up being recursive so that we can get our information back up the tree by recursing. And that's how they work. The complexity of pointer-based implementation, let's look through those. Most of these things are similar to the way that we're in the contiguous, but we'll look at some distinctions there. So we say that inserting a key in the best case and worst case is still constant time and linear. Best case, there's an empty pointer, we just stick it there. Worst case, we got to travel all the pointers that we have to find the next empty pointer and drop that thing there. Remove a key, of course, involves finding the thing, which makes me have to do, in the worst case, a linear search. Parent now can only be done in linear time. That's the distinction there. You see, that's why it's underlined, the distinction between our contiguous versus our connected, our array version versus our pointer version. Linear time, because the only way to find the parent of a node is to look at all of the other nodes and say, hey, are you pointing to the node whose parent I'm looking for? And if they are, then that's how you find the parent. If they aren't, then you move on to the next node, possibly looking at all of them. Finding the child is, of course, constant time. You can just look down on one of those pointers. Space is now evened up to be a linear amount of time all the time. We only have nodes for nodes that exist. We have pointers off to null pointers for places where spaces exist, and we don't have to instantiate whole nodes where there's no data. So our space has gone up a little bit in terms of overall overhead, because now each data item has its 2 pointers that are attached to it. So in our 64-bit machine, that's an additional 16 bytes that are attached to every node. But I don't have any blank nodes when I don't need them. So the space is now big O of n, even though it's a larger constant on that n. This is another way to do it, and this one that is not so common. This one has the parent in it. So we'll see that all this is just a simplification of that, but it's included that 3rd pointer there. So we've got a parent pointer, a left and a right pointer. In the case of the root, we would make sure that that parent pointer is pointing to null pointer. And anytime we get to an external node, we have the left and right pointers on this one and the previous version. Anytime we get to a leaf node, those left and right pointers are also null pointers. That's how we know to stop. I mentioned earlier that we could take any non-binary tree and convert it into a binary tree. And that was what we did when we wrote the pairing heap. We had this concept of a leftmost child, which was a new generation, and then a pointer to a bunch of siblings, right? We also had the parent pointer because we had to do so much up and down traversal in the pairing heap. But in general, that was a binary tree, because what we're thinking of down here, we think of as our left pointer was the one to a new generation, and then the right pointer was a pointer to a bunch of siblings. So if you think about the way that the pairing heap objects work, the nodes there had a left child and a sibling pointer. And that was that allowed us to have these nodes that had 2 important pointers all the time, even though it allowed us to represent a a pairing heap that might have had 10 or 50 or more children in a particular generation. It wasn't limited to 2 children only per node. We'd have any number of children. We accomplished that by taking left pointers as new generation and right pointers as a way to connect all of the siblings in a given generation. So this particular algorithm is going to take some general tree T and turn it into this T prime, which is a binary tree. And all we're going to do is look at each set of siblings and then take the first sibling, that's the leftmost child, and make that become the child of the node above it. And then the remaining siblings, the V2 through VK, all become a chain of right children, kind of like a linked list where we're sibling to sibling to sibling to sibling. That's how we get across. And then we just recurse on that, and you can convert any tree into a binary tree. That's a good question there, Andrew. What's the difference between template with type name and class? Those 2 words are, at this point in C++, they're just complete synonyms. You can use either one. There's no distinction between template and, between type name and class anymore. So here is that tree that we used from the previous quiz. And there we go, it's there. So what we're going to do is try to convert this into a binary tree, and this one's all animated out here. So we see that we're going to take that as our root, and then it's got a left child there to B. That's where we're going to go left. It's got 3 siblings, C and D, so they come off of B to the right. E has a child and sibling F, and we pull off F's children, I, J, and K, as a left child of F being I, and then the right child chain, J and K, show that next generation. So this is a binary tree now. If you look at it on the right, we see no node having more than 2 children. Most nodes only have 1 child. In fact, But we do have B and C having 2 children, but all the rest of them are now single child or leaf nodes. So this is now then converted to a binary tree. All right, that's our binary tree. Let's talk about tree traversals now. Tree traversal is one where you process the nodes in a tree. And by processing a node, I mean, we would also call it visiting a node. It allows you to do something with the data that's in that node. So every tree traversal we have is some systematic method of looking at all of these nodes. There's 4 that we're going to look at. 3 of them are very similar. We'll call those depth first traversals. They are the pre-order traversal, the in-order traversal, and the post-order traversal. Then the one that's different is the level order traversal, and we'll talk about that one at the end. But let's start with these pre-order, in-order, and post-orders. They all have something in common. They have a recursive call to the method, right? So in a pre-order traversal, I'm going to recursively do a pre-order traversal. And then I'm going to recursively do another pre-order traversal. In an in-order traversal, I'm going to do a recursive in-order traversal and another recursive in-order traversal. So what distinguishes pre-order from in-order from post-order is when we actually process or visit the node itself. In the pre-order, we visit the node first. We do that before we do the recursing. With the post-order, it's the exact opposite. We're going to recurse first, and then after we're done with all the recursions, we're going to visit the node itself. The in-order version works well with binary trees because we've got the distinct left half, right half version of it, and we can visit the node in order in between those two. It's worth pointing out here that no matter which traversal we're using, pre-order, in-order, or post-order, we're always going to visit left first and then right. Or sorry, we're going to recurse into left first and then we're going to recurse into right. So in pre-order steps 2 and 3, we recursively visit left, then we recursively visit right. In in-order steps 1 and 3, we recursively visit left and then we recursively visit right. In post-order steps 1 and 2, we recursively visit left and then we recursively visit right. And it's just the fact that the visitation of the node is step 1 in the pre-order, step 2 in the in-order, and step 3 in the post-order. And that allows us to do everything. These 3 are called depth-first searches because we end up, because of the way the recursion works, we end up working our way down to the bottom of the tree before we move across. You can see it pretty obviously here with in order because we recursively visit the left subtree, and then the first thing it does is goes to the left subtree, and the first thing it does is goes to the left subtree, and the first thing it does is goes to the left subtree until it can't go to left subtree anymore. That gets us down to the bottom as fast as is possible. The pre-order has us processing the node first, but then the very next step is work your way left. So we still end up getting, even though we've visited all of those nodes on the way down, we've worked our way all the way down left before we've done anything that moves across. And in the post order, it's the same as well. Level order now is one where we're going to look at things from the root and process that. Then we're going to process the children of the root. Then we're going to process the children of the root's children or the root's grandchildren. Then we're going to process the great-grandchildren and so on. In a level order, it sounds just like it is. You're processing these things one level at a time. And that processing, just like in the other traversals, is going to happen from left to right. Top down first, left to right second. Here are really simple, quick versions, and these all compile and work, of those 3 depth-first search traversals. We've got our node definition here in lines 1 through 6. Lines 7 through 12 is the pre-order traversal. It's passed in a node pointer. If the node pointer is null, then we're done. That's our base case. This is a recursive function because pre-order defined in line 7 calls pre-order in lines 10 and 11. We can't have a recursive function without a base case. Base case says if the pointer is dead, we're done. We visit the key first, and then we do our 2 pre-order traversals. In the post order, it's just flipped around those last 3 lines. So everything else is the same. We go post order in 15, post order in 16, and then visit the key in 17. With in order, we do the visitation in the middle. So we'll do in order in 21, visit in 22, and then in order to the right in 23. But all of these go left, right here in 10 and 11, left, right, 15, 16, left, right, 21 and 23. So it's always processed left to right. Here's our summary of these tree traversals. We've got pre-order, in-order, and post-order. I said those are all depth-first traversals. And we've also got the level order, which is a breadth-first traversal. Small tidbit here. That first project we did, project 1, that was a graph search. And we did a we did a depth-first traversal when we say, I'm going to look at all of the things around me and put them into a stack. And then I'm going to take something out of the stack and look at all of those things. So that was a depth-first traversal. The depth-first traversals and stacks are synonymous. We also, when we did the Q version, we did a level order, which we did a breadth-first traversal, right? And so in the case of that generic graph where we're working our way outwards from a particular location, that level order is, well, I'm going to first investigate the route, then I'm going to investigate everything that's 1 step away, then I'm going to investigate everything that's 2 steps away, then everything that's 3 steps away, then everything that's 4 steps away. That's my level order that I would be getting in a tree. It's also a level order search in a graph. We call that a breadth-first traversal because you're working across the entire breadth. Everything that's 1 away before you move to anything that's 2 away. And you do everything that's 2 away before you move to anything that's 3 away, and so on. So we've already done some depth-first traversals, and we've already done some breadth-first traversals in project 1. So let's try these and see if, given this tree here, we've got 0 at the root, its 2 children, 1 and 3, and then 1 has a left child of 2, 3 has a left child of 4. And the question is, what are the order of nodes visited using these 4 traversals? Pre-order, in-order, post-order, and level order. So in the pre-order traversal, remember, in the pre-order traversal, you process the node before you look to its children. So I will first deal with the 0. Then I move and recurse to the left here. That puts me at 1, and I'll process the 1 next before I move to its left, and I process the 2 after that. Once I've processed the 2 as 1's left, I can move to 1's right, but that's empty. But now 1 is completely done, and 0's left is completely done, so I can move to 0's right, which pre-order brings me to processing that 3 node. Then I process the 4 nodes. So the order of the nodes visitation of the nodes in this particular version with pre-order is 0, 1, 2, 3, 4. How about in order? So in order, we start at 0, but we don't visit 0 yet because we have to first recurse into its left subtree, which brings us over to the 1. And we didn't process the 1 yet because we have to recurse into its left subtree. Then it brings us down to the 2. 2 having no subtrees says now I try to go to the left subtree. There's nothing there. I can process the 2. Then I try to go to 2's right subtree. There's nothing there, and so I'm done. So I'm going to process that 2 as the very first thing that gets processed in order. I work my way back up the tree from there. Since now I've processed 1's entire left subtree, that's the one that starts at 2, I can process the 1, that's the next node processed, and the 1 has no right subtree, so I'm done. Once the entire left subtree is 0 is done, because 1 is processed, I can now process the 0. So the in-order traversal gives me 2, 1, 0, and I work my way to the other side, and I can't process the 3 before I process its left child, so I process the 4 before I process the 3. 2, 1, 0, 4, 3 is my in-order traversal. How about the post-order traversal? The post-order traversal, before I can process 0, I have to recurse into both its left side and its right side. So I'll go left first. I can't process the 1. I have to process the 2 because the 2 has no children, right? So I'll go to 2's left, it's empty, go to 2's right, it's empty, then I can process 2. So once again, my post-order traversal, the 2 is the first thing that gets processed. After I'm done processing the 2, I can process the 1's right child, which is empty. So that allows me to then process the 1 itself. So I start there with a 2, 1, much as I did in order. But now since I can't process the central node because I still have a right side to deal with, 0 doesn't come next. After that, I see that I break off to the right there, and what happens with 3? Since I'm doing post order, I can't process 3 before I process all of its children. I'll recurse to its left, it gives me the 4. There's no children of 4, so I'll process the 4. 3 has no children, so I'll process the 3. And now since both zeros left and right sides are processed, I can process the 0 last. So my post order traversal ends up as 2, 1, 4, 3, 0. It's important to note here that in these depth first traversals, where does that 0, where does the root show up? We see that in pre-order, the root is first. In post order, the root is last. And then in order, the root is exactly in the middle. That seems like an oversimplification. It turns out that root is processed at some relationship to the total number of items on the right-hand side and on the left-hand side. Since there's an equal number of things on the left-hand side and the right-hand side, the 0 in this case is processed directly in the middle. But if I had 10 items in the left subtree and 5 items in the right subtree, that 0 would be at that location. After the 10 in the left, before the 5 in the right. So you can get some information from that when you look at a traversal. You can see some things. I can see, well, in the pre-order traversal, the root is 0. Without even looking at the tree, if I just give you a pre-order traversal and asked you, where is the root, you would be able to tell me. If I said, okay, here's a post-order traversal, what is the root? Without looking at the tree itself, just looking at the value, the order those values get processed in, you should be able to return the value that is the root. The in-order traversal is a bit more work there. We need more information. So that's coming up in the next slide here. But let's talk about this level order traversal. This one is pretty straightforward as well. First we process the root level, 0, then its children from left to right, 1 and 3, then their grandchildren from left to right, 2, followed by 4. So my overall level order traversal is 0, 1, 3, 2, 4. All right, here's the question I alluded to in the previous slide. Can you draw a binary tree from these two traversals? So here's a pre-order traversal, 7, 3, 6, 9, 8, 13, 27. There's an in-order traversal, and this is a traversal of the same tree. The in-order traversal goes 3, 6, 7, 8, 9, 13, 27. Now the question is, can you draw the one tree that has these two traversals with this information that's given? Well, what do we get for our quick shortcut from the previous slide? We said, well, the first node in the pre-order traversal is always the root. So I can tell you right away that the root is 7. And then I've got children of 7. Well, where is 3? Well, in the pre-order traversal, I know that it comes after 7, but I don't know much else. Because remember, with pre-order, first we process the node, then we recurse into the left, then we recurse into the right. So with just the pre-order traversal, that 3 could be to the left of the 7, it could be to the right of the 7. I wouldn't know. This is why I need two traversals to get this information together. So I'll start out with my 7 there, and then as I try to put where the 3 can go, I see that the 3 can go into either one of those two sides and still satisfy the pre-order traversal. However, the in-order traversal does not get satisfied that way. Because the in-order traversal doesn't get to process the 3 until it's processed its children, I see that, or sorry, I can't process the 7 until I've processed its children. I see that there's some children of 7 in its left side. And so that 3 being one of them needs to show up over here. All right, working my way through the pre-order traversal, up next is 6. And you'll see that I could put that 6 as the left child of 3. I could put that 6 as the right child of 3. I could put that 6 as the right child of 7 and still satisfy the pre-order traversal. But because 6 shows up in the in-order traversal before 7, it means that 6 has to be in 7's left-hand subtree. So I cannot put that 6 over on the right side of 7. I have to put it here somewhere below 3. Now, how do I decide which? Remember the recursive nature of our tree definition. So if I said that with the in-order traversal, 7 kind of sits in the middle of its subtrees. The 3 and 6 go to its left and everything else goes to its right. The same thing is true for the subtree rooted at 3. Where does 6 show up in the in-order traversal? Well, if I think of 3 as being the root of some subtree, or just the root of a tree, the fact that 6 shows up after 3 in the in-order traversal means that 6 has to be in the right-hand subtree of 3. And so 6 gets put there, and since we've already gone to the right-hand side of 3, I know then that I can never have to worry about putting something in to the left of 3 anymore, because we've already got the 6 in that pre-order traversal saying, hey, we've gone right of 3. All right, so now as I put 9 out there, where can I put 9? I can put 9 below 6, left or right. I can put 9 below 7 and satisfy the pre-order tree. But what do we see in the in-order? The in-order traversal has the 9 after the 7, which means that the 9 has to be in the 7's right subtree, which allows me to say I can eliminate that. I can eliminate that as a subchild, a left subtree of 3, because I know that it comes after 3 in the in-order traversal, so it cannot be to the right of 3. These are my only 3 options for 9, and because it comes after the 6 in the in-order traversal, I know that the 9 goes over there. All right, that's great. Now, how about the next one? Where can we insert the 8? Well, I know that I've already started recursing into 7's right subtree, so that 8 has to be on the right-hand side of 7. It could be on either side of the 9, but it could be on neither side of the 6. So we've pulled those 2 pointers and given us the only 2 pointers that give us options here. And I'll have to figure out where that goes by using the in-order traversal. And looking at it, I'll see that 8 comes before the 9 in the in-order traversal, so it has to be in its left subtree. And since there's only one place to be in the left subtree, that's where 8 goes. Up next is 13 and 27. Those follow a pace just as we had done the previous stuff. We know that 13 has to come below either the 9 on the right or the 8 on the left or right. Because of the in-order traversal, it looks like it's in 9's right subtree, so we're just going to stick the 13 over there. And then a 27 has a chance of be either one of the children of 13. Of course, it shows up after 13 in the in-order, so it shows up on the right of 13. This is what is the only tree that can give us these 2 traversals. This is the only binary tree that gives us this pre-order and in-order traversal and gives you those values. All right, write an iterative function to do a level order traversal. Can you do that? Print the key at each node. Give you a minute or so to deal with this one. How do you write a function to do a level order traversal? Remember, process the root, then process all of the children, then process all the children's children, and so on and so on. Iterative, of course, means with a loop, not with recursion. That's all the time I got for you on this one. Let's dive into it. We've already seen this particular mechanism a couple of times. Once as the heart of the Project 1 algorithm, let's take some container, we'll seed the container by putting a value in there, and then we'll pull out that value. We'll pull values out of the container as long as they exist, and anything that's adjacent to that value we're going to put back in the container. We did that by pushing the northeast, southwest around a particular location back into the search container. We also did that with much of our work inside the pairing heap. I pushed the root node in there and I pulled it out. If it had something around it, what could be around it? If it had a child, push a child. If it had a sibling, push a sibling. It's the same algorithm. So this iterative traversal is going to work the same way. We're going to be using a queue to make this happen. That's what keeps it level order. But then all we have to do is push in the root, and as I pull the root out, if there's anything that is adjacent to it. This is of course going to be a left child and a right child. If those two exist, I push them back in the container. So I'll start by seeding the root node. This is a recursive function, so level order is going to call, it's not a recursive function, I take that back, this is an iterative traversal. So there's no calls to level order. I've got this null pointer protection though to make sure that I'm done when I'm done, and nobody slips me an empty tree. But I'm going to take that root and stick it into this queue, and then every time that thing has a child, so I'm going to push a child. So I'll pull that thing out with a front and a pop, and then print it because we're supposed to process it. If it has a child, push a child. If it has a child, push a child. In this case, I'm working my way from left to right because that's the way the traversal works. So if that node has a left, I push the left. If the node has a right, I push the right. If any time I've got something that ends, then that sort of snips that. This is this is iterative because we're in a while loop here, just a loop. This is going to get me through processing every node of the tree in a level order fashion. And that's the entire bit there. So that's a good thing to remember, that one of these ways that we traverse a problem space, especially when we don't know what the general topography is. We don't know if every point in our 2D puzzle has a left, a northeast, southwest. So I can't just write that as a standard for every time, because some of those things are edges. Same thing with the tree. I can't be aware of how many levels there are or how many children at every level. So what I do is I take some container, seed the container, and let the container control the search. As long as there's work to be done, I'll pull it out. So this was done with the copy constructor, with update priorities, with the destructor in project 2 with the pairing heap. It was also, like I said, the heart of the way that we did project 1. So this is a nifty base algorithm that you'll probably use many times in your career. Those are my tree traversals. Let's move on to the next one. Now we're looking at search. Of course, search is something that we've all done before. You're looking around for things. I've been fully involved in search for the last, I don't know, several months. It's just only intensified in the last week. I moved, and everything I own is in a box somewhere. I got a whole lot of linear searches, but hopefully I'm getting my life applied to computer science, right? With proper labeling, that's my hash table, right? I don't need to linear search every box to find a pair of socks. I need to hash my way to the box that has my clothing in it from the dresser, and then I just do a linear search of that box, and I've saved myself a ton of work, but that's my life. So search is something that we're pretty in touch with. Retrieval of a particular piece of information from some large collection of a whole bunch of stuff. Usually we want to be able to find all the information given some small key. We don't want to just find the key, because if we got the key to look for the key, we already have the key. That's not new news. What we want is all the rest of the data that's associated with it. So we know already that just doing a linear search in an array or a linked list is big O of n. That's great. We can search or insert, even if we want to keep things in a sorted fashion. We can do that in the worst case linear time. Even a hash table has a worst case linear. What if we wanted to go for something that was different, right? We talked about the hash table being the unordered map. This question at the bottom says, what if the order is important? As I look for things, what if order in the way that I've stored them is important, or order in the way that I use them later on is important? Enter the symbol table again. The symbol table is something we use when we talked about the dictionary. It allows us to do some things like insert and search, and of course remove from time to time. But those are the three fundamentals. Can I put something new in there? And then can I find something that has that key? Remove, of course, is the next best thing when you've got some data that might be non-static. We got things coming and going. We need to be able to remove things. After that, these other things are things that we might like to do, but might not be necessary all the time. Sort the symbol table. select an item with the kth largest key, or join two symbol tables. We had these three options as things we might do with a dictionary as well. The symbol table and the dictionary are pretty much synonymous. We have some value that lets us find a collection of data. We also want to do stuff like construct, test of empty, destroy, copy, check size, and blah, blah, blah. But we're going to be looking at the symbol table as we extend this into binary search trees. So, search, of course, combined with trees, and we'll keep this simple with binary trees. It gives us the BST, or the binary search tree. And here is what we refer to as the binary search tree property. This one says that the keys in a binary search tree satisfy this property when the key of any node is always greater than all of the nodes in its left subtree and less than or equal to the keys of all the nodes in a right subtree. So we've got a root. It's got to be greater than everything to the left, and it can't be larger than anything to the right. So we'll say it's greater than everything over here, and it's less than or equal to everything to the right. What this gives us is the fact that insert is as easy and as fast to implement as search. That's an essential property of the binary search tree, because if we keep this binary search tree property, then we can find where an item goes to insert it or to search in the same amount of time. Here are a couple of binary search trees. They've got 6 nodes each, and those values, both trees, are a couple of 5s, 6, 7, and 8. These two vastly different looking trees have the same information in them, and they both keep that binary search tree property going. On the left tree, we see it's rooted at 6, so the 7 and the 8 have to be to the right. The 2 and the couple of 5s have to be to the left. And it's okay to have duplicates. We see here that the duplicate 5 ends up in 5's right subtree. Given the definition we have here, the key of any node is less than or equal to all the nodes in its right subtree. This tells us that if I've got a duplicate here, that 5 has to be to the right of the 5. I would never find a 5 in the left-hand subtree of another 5. So that's one version of this tree. The other version looks like we started by inserting the 2 first because it's rooted with a 2. Since 2 is the smallest value, all of the other values in the tree have to be to its right subtree. There I see the couple of 5s, the 6, 7, and 8. And just as before when I talked about having 2 5s, I find that the lower 5 has to be in the right subtree of the upper 5. And even though they're not close, we've got 5 with a right subchild of 7 that has a left subchild of 6 that has a left subchild of 5, but that second 5 is in the first 5's right subtree, and that's very important. But these two trees have the same 6 nodes, just differently structured, but they are both legal binary search trees, and that's important to recognize that the order of the data, the order of insertion into a binary search tree will change the structure of the binary search tree. So here are our previous depth for search traversals, in order, pre-order, and post-order. Write out the output for the in-order, pre-order, and post-order traversals of this BST. And if you hadn't noticed there, that lower level 5 is now underlined. So when the values are put out there, that underlining is going to help show you where that 5 was processed. So you can see the 5 that's not underlined and the 5 that is underlined, and this is how we distinguish between those two. So with the in-order traversal, it looks like 2 followed by 5 followed by the underscored 5, then 6, 7, and 8. In the pre-order traversal, right? Remember, in the pre-order traversal, that's the one where we process the root node first. So the pre-order traversal has 6 followed by 5, and then 2, the underscored 5, then 7, then 8. And then lastly, we've got the post-order traversal with the 6, the root, showing up last there, and the post-order traversal always has the lowest leftmost item, the leftmost lowest item. No, it's the lowest leftmost item. There we go. That's the first one. So the post-order traversal starts with 2, the underscored 5 now, and then the normal 5, 6, and 7 and 8 from the right-hand side come out in that post-order order, which is 8 first, the lowest one, followed by 7, followed by 6. So our post-order traversal gives us 2, the underscored 5, 5, 8, 7, and then 6. Hopefully that makes sense. This is a great slide to come back to make sure that you're very much in touch with the way that pre-order, in-order, and post-order work. How about this question? Sort with a binary search tree. How can I sort using a binary search tree? The answer is on the previous slide, of course. If we look at those 3 traversals, an in-order traversal of a binary search tree is a sorted list. Isn't that amazing? So here, to do sort with a binary search tree, all I have to do is apply an in-order traversal. That's great. How about search? When we're trying to find a key in a binary search tree, how do I do it? This function that is being requested, called tree search, returns a node pointer with the node that has the key K that's given, if it exists. If the key that's being looked up does not exist in the tree, then this function should just return the null pointer. And of course the BST property is copied down there, and that's how this is going to go. Then the following question is, what are the average and worst case complexities of tree search? There's a couple of different ways we could write tree search, but this first version does it iteratively. We've got a while loop that controls everything, so we see while x is not the null pointer. We're always done looking at pointers when we've got a null pointer. While x is not the null pointer, then I can check its key. So if the key of x is not equal to k, then I have not found what I'm looking for. So as long as I've got something to look for and I'm not looking at what I'm looking for, I've got work to do. That's what this while loop says. If you've got something to work on and it's not what you're looking at, or not what you're looking for, then keep going. If I fall out of this, in either case, that while loop is going to have me return x. So if there was nothing I was looking at, that's the null pointer, then I return the null pointer. It means I didn't find the thing. But if I did have something, I can fall out of this loop if what I'm looking at is what I'm looking for. In that case, return it. That's what line 10 does. Inside of the while loop, we're just checking to see which way we should go because we've got this binary search tree. If what I'm looking at is not what I'm looking for, then I have to decide, well, if what I'm looking at is what I'm looking for is less than what I'm looking at, then I need to go into the left-hand side. So that changes x to be equal to x's left. Otherwise, since we know that it's not equal, it must be in the other side. That sets x equal to x's right. So this is an iterative way to do a tree search. You could write this same function recursively. Ta-da! The recursive version. Here we see that tree search declared in line 3 has calls to tree search in lines 7 and 8. That's the recursion I was talking about. So the only way that we can get recursion is if we got a base case. Our base case there happens in lines 4 and 5. If what I'm looking at is a null pointer, then be done. Or if what I'm looking at is what I'm looking for, be done. In either case, return that thing. It's either the null pointer or what I wanted. That's my base case. This gets me out. Otherwise, I'm going to do that same sort of thing. If what I'm looking for is less than what I'm looking at, I'm going to recurse into the left-hand side. If what I'm looking for is greater than what I'm looking at, I'm going to recurse into the right side. So here's our search example with the tree here. We're searching for 8 given the root. How do I do this? I look at 15. I see that, 15. I'm looking for 9. Well, 9 is less than 15. Let's go to the left. And now I'm looking at 6. I see that 9 is not less than 6. Let's go to the right. That puts me at 7. 9 is not less than 7. So I go right again. That puts me at 13. And since 9 is less than 13, I want to look left. There is where I find the 9. That's tree search. The complexity now, we think of this in terms of the height of the tree, the maximum height of the tree. We'll say that the complexity of this search, because I only need to go from the top to the bottom, wherever I find the bottom, that's the worst I have to do to search. I never have to go back up and say, well, this was kind of a dead end, let's go search somewhere else. We can tell that because of the BST property, well, if what I'm looking for is less than what I'm looking at, everything to the right of what I'm looking at, I can eliminate. I know that what I'm looking for must be over here to the left. So we can do this search without ever having to go back. So then the complexity of the search is just the overall height of the tree, the maximum height of the tree. So my average case complexity there has to do with how balanced my tree is, how dense it is stored there. My average case complexity looks like log n. That's as dense as I can have this tree. In a very balanced tree, I end up with something that's log n depth. And the worst case is a stick tree, and all the other trees fall somewhere between log n and big O of n. How about insert? How do we insert a new key into the tree? Well, it's similar to search because I'm going to use that search to figure out where the item should belong, so the next time I try to find it, I can find it similarly. So I'm just going to use my search algorithm to go to that location until I find a null pointer. As soon as I find a null pointer, then I append the new node. Let's take that previous tree and we're going to insert 15 at the root. So I've already got a root of 15, so which direction do I want to travel? Well, 15 is not less than 15, so if I was searching for another 15, I would go to 15's right. 15 is less than 18, so I go to its left. 15 is less than 17, so go to its left as well, and that is where the new 15 gets inserted. You can play around with this version and add different values and figure out where to put those, but this is a good slide to do some tree insertion practice with. This one is important here. We talk about dealing with trees with duplicates. Depending on your application, you may or may not have to handle duplicates. When there are no duplicates, then our binary search tree property just gets a little simpler. We say everything to the left is less than, everything to the right is greater than. That's no duplicates. When we do have duplicates, we have to figure out where to put it, and we see that we've done this STL style, right? The STL style is, well, if I can define one comparison operator, let it be less than. So I can say if this is less than, it goes over there. If it's not, it goes over there. So in that way, when I've got duplicates, that's why I find that things to the left are less than and things to the right are greater than or equal to, because that's the opposite of less than. The opposite of less than is greater than or equal to, so that's where I find things to the right there. That's how my BST property gets written. So that's how we do it in the slides. That's how you can expect it to be done in the STL. We could have done it the other way, right? We could have said everything to the left is less than or equal to, so duplicates go to the left-hand side and non-duplicates go to the right, because everything to the right has to be greater than. So we had those two choices, and we went with a simple one, which is let's just use the one operator that we're used to using, which is the operator less than. So here's how tree insert would work. This is a recursive version of this, and we can see that tree insert that's defined in line 1 calls tree insert in lines 5 and 7. And even though there's 2 calls of tree insert, since only one of them happens, and it's the very last thing that gets done, this is actually a tail recursive insertion. So this one works just as efficiently as an iterative version would be done. I would suggest that you try writing an iterative version just to make sure that you understand the translation between recursive and iterative. You can write an iterative version of tree insert pretty easily. But it is recursive in 5 and 7. Can't work then without a base case. My base case is if x is a null pointer, or I'm trying to insert something, if x is a null pointer, I've found where this goes. I'm going to set x equal to this new node, and I'm going to put the value k into the constructor there, and so that's how I put it in there. The new node is always inserted at a leaf. Wherever I find that null pointer, that's where it is. So if I start out with an empty tree, the first thing I see is a null pointer. I'm going to put the node there. Otherwise, I'm going to keep the BST property alive with these two recursive calls, because if what I'm looking to insert, K, is less than what I'm looking at, then I need to insert K in the left-hand side. So I'll call tree insert with that node's left child. Or I'm going to put it in the right-hand side because it's not less than. In this case, it must be greater than or equal to. There we go. So that's how it does. Now, one thing I want to talk to you about before we leave this slide is that first parameter of tree insert. Look at it. It is a node star ampersand X. Now, what is that? That is a reference to a pointer to a node. Okay? A reference to a pointer to a node, because pointers are integers. Okay? That shouldn't be a surprise. Everything in the computer that we have is an integer. Really binary integer, because it's all a bunch of bits and ones and zeros. But pointers are an address. So if you think of the address of your dorm room or the address of your home, it's just a number. I live on a street, my address is number 40. So if I give you the number 40, you wanted to do math on it, you could say, well, I can take my own copy of this 40 and double it, and I would have 80. And we're used to that with integers. When we pass an integer by value, we're used to being able to change that integer in the called function and not have any effects back in the local location. So the same thing is going on here with this tree insert. Now, if I pass a pointer and you change that pointer value locally, not what the pointer is pointing at, just the address itself. Now, you haven't changed anything in the calling function, which is why this pointer is being passed by reference. The pointer being passed by reference means that changes in this function change that pointer value in the calling function. So what that pointer is pointing at. So here you think of me calling this function originally with some null pointer root pointer. Now, that root pointer is some address, and it's pointing to null. If you want to change what that root pointer is pointing at, you cannot change a copy of that pointer, because if I send you a copy of that pointer, which would happen if I pass the pointer into this function by value, you'd be getting a copy of that pointer. Any changes you made to that copy of the pointer would not affect that pointer at the calling location. So we've passed in the pointer by reference so that changes in the called function affect changes in the calling function. This is the only way that we can set this X equal to a new node K, right? We set X equal to a new node K, that changes the calling function's root pointer. So this allows us to make actual structural changes. And that's why we've got that pointer, that reference to pointer to X. So here's an exercise. Let's start with an empty tree. Insert these keys in this order: 12, 5, 18, 2, 9, 15, 19, 17, 13. Draw the tree. Right? Start with an empty tree. And when I say draw the tree, what I'm talking about here is draw a binary search tree. Write the new order that I can use to insert the same keys. So I want to take these same keys and put them into now a tree that's a worst case tree. Then there's another question that says, how many worst case trees are possible for some list of n unique values? So that's the abstract question there. All right? How does this look? There's my tree. I've inserted 12. 5 is less than 12, so it goes to the left. Put it there. 18 is not less than 12. It goes to the right. 2 is less than 12, less than 5. It goes to the left, goes to the left. 9 is less than 12, but not less than 5. It goes left and then right. 15 is not less than 12, we go left. Less than 18, we go, sorry, not less than 12, we go right. Less than 18, we go left. And that's where we find the 15. 19, not less than 12, not less than 18, a couple of rights, and that's where the 19 is. 17 is not less than 12, less than 18, not less than 15. So we go right, then left, then right, and that's where 17 belongs. And lastly, 13, which is not less than 12, but it is less than 18 and 15. So we go right once and then a couple of lefts, and that's where the 13 is located. Here's one new order that we can use to insert the same keys. That's going to generate a worst case tree. This order goes 2, 5, 9, 12, 13, 15, 17, 18, 19. If you're paying close attention, you'll notice that all of those are in order. So this is going to give me a tree with 2 at the root, 5 which is larger to the right, 9 is larger to its right, 12 is larger to its right, 13 right. So this is what we call a stick. It's a tree, but it's just one long piece. There's no branching that goes on. So this is a stick tree, and the last question there that's unanswered is how many different stick trees are there? Because you might say, well, this is a worst case tree. This is, you know, it's one worst case tree. There's a lot of trees I could make there. Or, well, if I sort them in the opposite direction, it would go 19, 18, 17, 15. I could have the other stick, but there's 2 sticks, and there's a lot of different ways I could do this. Turns out there's more than 2 sticks, because what if I went right, left? That's still a stick, because even though it has a bend in it, it doesn't have a split, it doesn't have a fork. So it still ends up being of height n. So the question is, how many height n legal binary search trees can I make given a set of data? We get down into taking some of our choices here. It turns out that at every level, I've got a choice to make. At every insertion, if I can insert the largest item, I'm sure to go down without forking. The largest remaining item, I'm sure to go down without forking. If I can insert the smallest remaining item, I'm sure to go down without forking. So at every decision I have, I can take the largest remaining or the smallest remaining. I can do that n-1 times. So I end up with 2 to the n-1 different trees, because the last node has to go, well, we start with some node, it has to go at the top. Then there's n-1 times I can pick the largest remaining or the smallest remaining, and I end up with this thing that looks like 2 to the n-1 total worst case trees, which is now important. You see, well 2 to the n-1, that's a large number of worst case trees, because all of those 2 to the n-1 trees have a height of n. That's worst case. We're looking for something to be log n. That's why we go BST in the first place. So this is why, you know, we would just use BSTs all the time if we were just concerned with just the one greater than stick or the one less than stick. If there was only 2 worst case trees, then most of the time we'd be doing great. But there's a lot of times that it can go bad. The complexity of insert and many of our other tree functions usually depends on the height of the tree. We talked about the average case when it's fairly balanced. We call that a log n. And the worst case where it got unbalanced, where it looks like a stick, we don't have much branching at all, that could be linear. So somewhere between log n and big O of n, that's where we're going to find all of our tree work. In the average case with random data, it's usually pretty well balanced. Somewhere between log n and 2 log n in depth is where you find on average case with random data. And that's not too bad. All right, here's an exercise. Write a function to find a node with the smallest key. And then what are the average and worst case complexities? How do we find the smallest key? I'm going to give you a minute to think about that one. I need to check my slide count. Man, I lost my page there. All right. Write a function to find the node with the smallest key. Now that's pretty easy in a binary search tree. It'll just keep going left. Tree min is just go left until you can't go left anymore, and then you're looking at the smallest node that's there. All right, so I'm going to throw this one up there, and then we're going to take the break. All right. This is tree min. And you see here, we've got a nice iterative version here. We're using left. And as I mentioned before, anytime we write a function here, most of these functions can be written recursively because of the recursive definition. So if we write a function recursively, see if you can write it iteratively. If we write a function iteratively, see if you can write it recursively. So here's an iterative version of tree min. Make sure you understand it. Then turn around and write a recursive version of tree min. Then answer the question, is this tail recursive? Are these two exactly equivalent in time and memory? So this one is pretty straightforward. If x is a null pointer, then we've found an empty tree. We've got nothing to do there. While x has a left, I'm going to set x equal to x left. As soon as x has no left, I've found the smallest item in the tree. So we return that. Our average case complexity, of course, is because of the average case of the height of the tree. That's a log n. The worst case is linear. So this is tree min. Good place to break. I'm ready for lunch. Take everything that we've written here today and make sure that you can write it both iteratively and recursively. If we've written it one way, you write it the other. All right? I'll see you tomorrow.